Greetings, school learners. I hope that the learning is coming across really well. So, last time we talked about the assumptions, axioms, and postulates, and we were going to continue into the claims right now. The claims, well, we are going to extract the claims out of the axioms or the assumptions. How? Well, I wanted to keep this canvas really empty because I wanted to use this section and then go back and forth in explaining how these two combine to give us a certain claim and these two combine to give us a certain claim. But okay, we'll work around that. Last time, we had these two assumptions that matter is made up of particles, also that they are in motion. So, what did we come up with? We came up with a discrete random motion. I introduced this word random motion just now, never before. What does random mean? Something you cannot predict. The particles are moving haphazardly, and yes, okay, the container is gonna restrict them, for example, in water or in some other gas. But other than that, there's going to be random motion, even if they are vibrating, and we are gonna talk about when the vibration happens. So let me write that down. Secondly, we were talking about interactions. So matter is going to interact, is it not? I mean, now you are considering spherical particles. It will happen every now and then that this particle is going to come over here and hit this particle. And in doing so, you can imagine a large or very speedy ball attacking a slower or stationary ball and giving it some momentum or giving it some velocity. So that is going to happen. So there is going to be interaction between these particles. That is another claim. Okay, thirdly, using the second claim, we are going to say that only the average velocity of the particles are going to decide what the temperature is going to be. And you're going to say, whoa, isn't the entirety of, the particles going to be at the same velocity? And I'm going to say, no. Just like this example, a particle hits this other particle and gives it essentially some extra velocity. So there are going to be some particles which are going to move by the size of the arrow. You should understand what I mean, which are going to move either slower or either speedier. But the overall or the average velocity is going to be the decider. And consider this as a supplementary claim. We did talk about it a little bit. Other than freezing, that is solidifying, melting, boiling, or condensing, and I did not use the word condensing before, it was just the process of the steam converting back into the water. So we're going to write this as a supplementary claim that other than the state change, velocity will be dependent on temperature. This is how we write it. Or basically, the temperature is going to be dependent on velocity. This parenthesis and inside putting the temperature, or this parenthesis and inside putting the velocity, is basically just saying that. Now we touched on this next claim a little bit in the last video. If these particles are in random motion, does that mean that my rock is gonna move through the room and interact with my nose? No. So what is keeping that rock in place? Well, there are forces, attractive forces between molecules called intermolecular forces, and there have to be these intermolecular forces. Why else would these particles moving at certain speed stay in this bulk of material called a rock? Similarly with water, there's a gray area in water. We are going to talk about and touch about it on evaporation, but certainly the same thing is going to happen with water as well. So, intermolecular forces are going to be in play. So, you can ask, does this have any influence or any consequences on our understanding? And well, yes. For example, we see droplets forming on a glass when it has extremely cold water. Well, not extremely cold, only cold will work as well. And we know that this is related to condensation. So basically, the cool surface of the glass is going to offer less violently moving particles to come here, adhere, or basically stick to the surface and become liquid. So we now do have a crude picture of what these are. And because of these, we know that there should be a way to categorize rock, water, and then any liquid. And why just keep it moving forth without actually defining what these are or how their arrangement and their motion going to determine what they physically would look like or feel like? So here I've copied this table from David Sang's book. I don't know why this is so blurry. Okay. Well, if you remember, the arrangement was going to be determined by the intermolecular forces. Well, it's also going to depend on whether the velocity is large enough to overcome these forces. The motion in itself reflects the velocity, which is basically dependent on the kinetic energy, which has a relation to temperature. I mean, we don't have an expression, but we get the gist. So, solids. The force is so high that there is a regular pack and stack and array of particles that can only move via vibrations. What does that mean? The velocity is going to be this to and fro motion, essentially sticking to this place. The to and fro motion of the vibrations isn't actually that large, and you can't actually blame the particles. The space is too low, and the intermolecular forces are very high. That is basically why they're in this shape. What about liquids then? Well, liquids have enough of a force on them that they keep them in a constant volume. Well, solids are in this tight pack together in a fixed volume structure. Water can, work its way around that. It's going to, move around. It's going to maintain a volume, but not a fixed shape. Now, the particles in water or any liquid have a way around that. They can move around, but they cannot diffuse into the atmosphere. So they maintain a fixed volume, but not a fixed shape. And why is that going to be? Because the random motion of the particles is something called translational. And I'm just adding up jargons? No, you should know this as physics students. Translation means object can be in this place and when it is moved to another place, say from here to here. For solids, this was a vibrational motion. That is, you do not deny that they are moving, but basically, if a particle's here and in a moment it's going to be displaced this much, in some other moment it's going to come back to this position and just go in the opposite direction or some other direction. There's going to be vibration, this to and fro motion. And now, what about the gas? Well, remember intermolecular forces? You can neglect these right now. And we're neglecting them? Yeah, we are neglecting them. So basically, what your particles are doing now, they are free. They don't have forces. So they're moving, they're moving, they're moving, and they continue to move. And only the shape of the container is going to restrict when they hit the wall. There are going to be instances where another particle is going to go and hit this one, and there's going to be interaction. Yeah, that is true. And there is a little bit force, but we're assuming that it's essentially none. So fixed shapes, particles being very closely stacked together. What is this? This is solid because of this close packing and this constant volume structure. Because of the large attractive intermolecular forces, there's only going to be vibrational motion. A liquid allows the particles to move past each other, but this force is still enough to keep a constant volume. That is, you leave a glass of water and it will not immediately become a part of the atmosphere. It is going to maintain its volume. So this is liquid. Some bit of space over here. And then gases, well, they are far apart, so the particles' forces don't influence each other that much. The velocity compared to that is pretty much high. So this is gas. The last influence on our understanding is that, hey, there exists this small world where you have smaller particles and you talk about their velocities and stuff. A concept you don't see in this larger world. I'm going to call it the macroscopic world. But in the microscopic world, there is going to be this quantity. Each particle is going to have a velocity. Well, these smaller velocities that we do not observe with our naked eye are going to give birth to this larger quantity called temperature of matter, of the material. So, although we are still in a crude world, I mean, we have come up across what states are, basically, essentially, the physical properties, but we're not done yet. And in the next video, we will be moving on to certain evidences and a deeper level of understanding than where we are now. Boy, I learned something out of that. Teaching you always makes me learn. And that's why we are co learners. Thank you for watching the video.